Hi everyone, welcome to my channel. Please like and subscribe. In this video, we'll be learning how to design a cantilever retaining wall which is subjected to a leaf surcharge. Now, let's go directly into our problem, which states that a cantilever retaining wall is subject to a leaf surcharge of 7.5 kN per meter square. The backfill consists of cohesionless soil of internal angle of friction of 30 degrees, and the unit weight of soil was 21 kN per meter cube. We are required to design for the steam. For the design of the steam, we are required to calculate the design bending moment due to the S pressure and the design moment due to the surcharge. C, we are required to determine how to calculate the main reinforcements. And D, we are required to determine the distribution reinforcements given that the cover is 35 mm and FU, which is reinforcement strength, which is 460 MPa, and concrete strength, which is FCU, is 25 MPa. The diameter of all reinforcement is 12 mm. Our figure of this cantilever retaining wall is this way. So we are required to design this. We are required to design this steam wall. Now let's start step by step. Now before going direct to the design, let's analyze our design data. Design data. We have given surcharge of 7.5. This is kilonewton per meter square. We have given internal angle of friction, which is 30 degrees, and the unit weight of soil, which is 21 kilonewton per meter cube. Also, we have given as a concrete cover of 35 millimeter. Also, we have given FCU, which is 25 MPa Newton per millimeter square. The reinforcement strength, which is FY, which is 460 MPa. Also, we have given the diameter of all reinforcement, which is 12 millimeter. Now let's start to design this steam wall. This is cantilever retaining wall, which is subject to surcharge of 7.5, and this is a steam of this cantilever retaining wall. This is steam, and this is toy. This is a slab which have toy slab. This is toy slab, and this is heel slab. The thickness of this steam, the thickness of this steam, this one is 0.25 meter. So its thickness of this steam is 0.25 meter, 0.25 meter, which is equal to 250 millimeter. Okay. After the next step is to draw. After that, we are supposed to draw the pressure diagram due to surcharge and due to the soil. So the backfill was this region. The backfill of this cantilever retaining wall was acting at this region. So this is the where the loads due to the heel slab acts. Now this is the pressure diagram. When the surcharge is subjected, it provides a uniform pressure diagram. Through the total weights of the steam. So the pressure diagram due to surcharge is uniform throughout the total height of the steam. So its pressure diagram is this way, and the pressure diagram due to the soil usually varies linearly. So the pressure diagram due to the soil is this one. The pressure diagram due to the soil is this one. And the pressure diagram due to surcharge, because surcharge provides uniform soil pressure diagram, so it will be this way in triangular. And due to the soil is this one. So this pressure diagram, this surcharge and soil pressure have disturbing force, horizontal force, which used to resist this soil and surcharge. So let's say this is horizontal force due to the soil. Let's say force one, and perpendicular distance from the base up, from the base up to where this horizontal force act is obtained by taking h, the height of this steam divided by 3, divided by 3, divided by 3. And also this surcharge, the pressure diagram due to surcharge is horizontal force which acts so as to resist this load due to surcharge. Let's say this is horizontal force due to surcharge. Let's say this is F2, and the total distance from the base up to where this horizontal force acts is obtained by taking h, the height of steam, divided by 2. Now, this is the pressure due to the soil is called active pressure. So this is where active pressure, and the pressure due to surcharge acting at this point, at this region, the pressure due to surcharge. After that, we are required before going direct to the design of this bending moment. Now let's find the value of active pressure. The value of active pressure that we will be use it for the design, for the calculation of this active pressure and the surcharge. Now, because the total height of this cantilever from the ground level up to the base was 3 meters. To obtain the height of this system, it will be equal to 3 meters minus the thickness of this base, which is 0.3 meters. So to obtain the height of steam, it will be equal to 2.7 meter. 2.7 meter. After that, let's find the coefficient of active pressure. Coefficient of active pressure is obtained by taking 1 minus sine internal angle of friction over 1 plus sine internal angle of friction. So for more simplification, it gives to be equal to tan square 45 minus internal angle of friction divided by 2. Now coefficient of active pressure will be equal to tan square 45 minus 30 divided by 2. This it will be equal to 1 over 3. So the coefficient of active pressure is 1 over 3. Now let's go in direct to the design. For A, we are required to design bending moment due to the S pressure. Designing moment due to the S pressure. This is the S pressure, S soil. So we are required to determine its bending moment, design moments. So A, design moment due to the S pressure, S soil, S pressure. To obtain the design moment to the S pressure, the first step is to find the pressure due to the soil, pressure due to the soil, pressure due to soil, pressure due to the soil, which is active pressure. Now, this active pressure is obtained by taking unit weight of soil times coefficient of active pressure times the height of steam. The height of steam. Now, let's substitute its value. The value of unit weight of soil is 21 times coefficient of active pressure, which is 1 over 3 times h, which is 2.7 meters. So when we compute this value, it will be equal to 21 times 1 over 3 times 2.7. It will be equal to It will be equal to 18.9. This is kilonewton per meter square. The next step is to find horizontal force due to the soil. Horizontal force due to the soil. Horizontal force due to the soil. This one, horizontal force due to the soil. Because the pressure diagram due to the soil is this one, which is triangle. So its horizontal force due to the soil is force 1. So force 1 is obtained by considering the area of this pressure diagram. The pressure diagram to the soil is triangular in nature. So the area of triangle is obtained by taking a half times weights or times the weights, which is active pressure, times height, which is the height of steam. So horizontal force, it will be equal to, which is force 1, it will be equal to a half times pressure due to the soil, which is 18.9 times H, which is 2.7 times 0.5 times 2.7. It will be equal to 25.52. This is kilonewton per meter. This is horizontal force due to the soil. The next is to determine the maximum moment due to the soil. Maximum moment occur at the base. Maximum moment. So to obtain this maximum moment due to the soil, is obtained by taking this horizontal force times perpendicular distance, because it's acting at the base of this retaining wall. So maximum moment due to the soil. Let's say this maximum moment 1 is obtained by taking horizontal force 1, which is force 1 times perpendicular distance, which is h divided by 3. Maximum moment due to the soil, which is maximum moment 1, it will be equal to 25.52 times 8, which is 2.7 divided by 3. It will be equal to 25.52 times 2.7 divided by 3. It will be equal to maximum moment 1 will be equal to 22.97. This is kilonewton per meter. The next, we were required to determine the design moment due to the S pressure. Design moment due to the S pressure. Let's say this is moment 1. This design moment is obtained by taking the maximum design moment times factor of safety due to the self-weight of the structure. Self-weight of the structure is due to the dead load. So to obtain this maximum design moment due to the soil is obtained by taking factor of safety due to dead load, which is 1.4 times maximum moment due to the soil. Now, when we substitute this value, it will be equal to 1.4 times 22.97. Maximum design moment due to the soil, it will be equal to 1.4 times 22.97. It will be equal to 32.16. This is kilonewton meter per meter. This is the design moment due to the soil. The next we are required to determine the design moment, which is the design moment due to surcharge. Design moment due to surcharge. Design moment due to surcharge. Due to surcharge. Now, to obtain design moment due to surcharge, the first step is to determine pressure due to surcharge. Pressure due to surcharge. This pressure due to surcharge is obtained by, let's say this is PQ. Pressure due to surcharge is this one. Pressure due to surcharge. The first step is determining this pressure due to surcharge. Now, this pressure due to surcharge is obtained by taking coefficients coefficient of active pressure times the value of surcharge. Now, pressure due to surcharge will be equal to coefficient of active pressure is 1 over 3 times surcharge, which is 7.5. Now, pressure due to surcharge will be equal to 7.5 divided by 3, it will be equal to 2.5. This is kilonewton per meter square. The next is to determine horizontal force due to surcharge. Horizontal force due to surcharge is this one, because this is a pressure diagram due to surcharge, which was uniform, because the surcharge provides uniform lateral pressure. So its pressure diagram is uniform throughout the total height. So the horizontal force due to surcharge is this one. And the horizontal force is obtained by taking the area of the pressure diagram. The area of pressure diagram of this pressure diagram due to surcharge is rectangular. So the area of rectangle is obtained by taking width times height. Width is pressure due to surcharge times h. So horizontal force, it will be equal to surcharge, which is 2.5 times h, which is 2.7. When we multiply here, horizontal force due to surcharge, it will be equal to 6.75. This is kilonewton per meter. The next is to determine the maximum moment due to surcharge. Maximum moment due to surcharge. Let's say this is the maximum moment 2. This is maximum moment. Also, maximum moment always occur at the base. And this maximum moment due to surcharge is obtained by taking the horizontal force due to surcharge times its perpendicular distance. This horizontal force due to surcharge times its perpendicular distance, which is h over 2, will obtain the maximum moment at this base due to the surcharge. So force 2 times h over 2. Maximum moment, which is maximum moment 2 due to surcharge, it will be equal to 6.75 times h, which is 2.7, divided by 2. Maximum moment due to surcharge 2, it will be equal to times 2.7 over 2. It will be equal to 9.11. This is kilonewton meter per meter. The next is to determine the design moment. Design moment due to surcharge. Design moment. Let's say this is moment 2. This design moment due to surcharge is obtained by taking factor of safety due to the leave surcharge times maximum moment due to surcharge, because this cantilever retaining wall was subjected to leave surcharge. So we multiply, so as to determine the design moment, we multiply by the factor of safety due to surcharge. Factor of safety due to surcharge, which due to the leave surcharge. Factor of safety, the factor of safety due to the leave or imposed load is 1.6 times maximum design moment due to surcharge, which is maximum moment 2. So design moment due to surcharge, it will be equal to 1.6 times 9.11. Design moment due to surcharge, it will be equal to 1.6 times 9.11. It will be equal to 14.58. This is kilonewton meter per meter. This is the question number B. Now, let's find question number C. Question number C, we are required to determine to calculate the main reinforcement. Main reinforcement. C, main reinforcement. Main reinforcement. We are required to determine the main reinforcement. This main reinforcement is obtained by taking the area of main reinforcement is obtained by taking maximum design moment of the steam over 0.87 FYZ. But how to determine this maximum design moment of the steam wall? This maximum design moment of the steam is obtained by taking design moments due to soil pressure, which is moment 1 plus design moment due to the surcharge, which is moment 2. Now, this design moment of the steam is obtained by taking maximum design moment due to the soil, which is 32.16 plus design moment due to surcharge, which is 14.58. So the total design moment will be equal to 32.16 plus 14.58. It will be equal to 46.74. This is kilonewton per meter. After determining the total design moment of the steam, now let's determine effective depths so as that will enable us to obtain the value of Z. Effective depth is obtained by taking the thickness of steam minus cover minus diameter, diameter of the reinforcement divided by 2. Effective depth. Now, the thickness of this steam, this is the thickness of the steam wall, which is 0.25 meter. In a millimeter, it will be equal to 250 millimeter. 250 millimeter minus cover, which is 35 minus diameter of all reinforcement, which was 12 millimeter. So we divide by 2. It will be equal to 250 minus 35 minus 6. It will be equal to 209 millimeters. This is effective depth. Now, after obtaining effective depth, let's find the value of K. The value of K is obtained by taking this design moment of the steam over FCU BD square. Now, the value of K will be equal to design moment is 46.74 exponent 6. This is kilonewton per meter. So to put it in newton per millimeter, so it will be, we multiply by 10 power 6 of SU. SU is 25 times beats, which is 1 meter, which is equal to 1000 times effective depth, which is 209 square. Now the value of K will be equal to 46.74 exponent 6 divided by 25 times 1000 times 29 square. It will be equal to 0.0428. This is the value of K. This value of K will enable us to determine the value of Z. Now let's go direct to the formula to the form that it will give us the value of Z. The value of Z is obtained by taking effective depth times 0.5 plus 0.25 minus K over 0.9. This should be less than equal to 0.95 D. If this value will be greater than this one, we take 0.95 times effective depth. So if it is less, we take the less one. Now let's substitute the value of K here. So the value of Z will be equal to 0.5 plus 0.25 minus the value of K, which is 0.0428 divided by 0.9 under root. So the value of Z it will be equal to divided by 0.9, 0.25 minus under root of ans plus 0.5. So it will be equal to 0.95 times effective depth. Now the value of Z it will be equal to 0.95 times the effective depth, which is 209. The value of Z it will be equal to 0.95 times 209. It will be equal to 199 millimeters. This is the value of Z. The next is to determine the area of main reinforcement. The area of main reinforcement is taken by design moment of the steam over 0.87 FYZ. Now let's substitute Its maximum design moment of the steam is 46.74. This one, 46.74. Exponent 6 in Newton per millimeter over 0.87 times Fy, which is 460 times the value of Z, which is 199. Now, the area of main reinforcement will be 46.74 exponent 6 divided by 0.87 times 460 times 199. It will be equal to 587. This is millimeter square per meter. This is area required. So to obtain the area that will be provided, we use the design table, which is a design table which provides the area per meter. This one, according to because the diameter for reinforcement was 12, so we come direct to the to the diameter. This design table shows the diameter and the spacing, so and the area to be provided. So according to the diameter of 12 millimeter, to obtain the area to be provided, we take the maximum area, the maximum area which is closer to this area. So the maximum area which is closer to 587, it will be from this one. It will be this one at a spacing of 175 millimeter. So we say that provides bars with diameter of 12 millimeter at a spacing of 175 millimeter. This is center to center, which provides the area of 646 millimeter square per meter. This is the area of main reinforcement. This area of main reinforcement for the steam wall occur at near face. When I say near face for the cantilever retaining wall, near face, this is a steam. So this area of main reinforcement provide at near face, these sides where there is soil. But to obtain the area at the front face, at this side, is due to the minimum area, which is distribution reinforcement, which is we are required to determine the design of distribution reinforcement that will give us the area at front face, the reinforcement at front face at this side. Now let's find the value of the distribution reinforcement. Distribution reinforcement. This distribution reinforcement is due to the minimum area. Which is obtained by taking 0.13 B times thickness of the steam. So the minimum area, it will be equal to 0.0016 times breadth, which is 1000, times the thickness, which is 256. So the minimum area, it will be equal to 0.0013 times 1000 times 250. It will be equal to 325 millimeter square per meter. This is area required. So the area to be provided, provides bars with diameter of 12 at a spacing of from the design table. This one is the maximum, which is close this one, at a spacing of 3 millimeter center to center, which gives the area of 375 millimeter square per meter. Thank you for watching this video. Please like and subscribe for more civil engineering tutorial. See you.